So I have to apologize right off the hop because my first slide is, or one of my slides is, Greg's was way better with that old adage, good, fast, cheap, or good, pick any two at the same time. But Greg's was way better. So I wanted to talk very briefly about contractors, and this is a system in my mind that shows some care and consideration that's gone into the installation, the layout of it, and it commands a bit of a premium. And mechanicals typically are a big line item when you're building a house. Now this is, it works, but it won't run. There's a number of issues that are wrong with it, but the homeowner had 3 quotes that were all in the $13,000 to $15,000 range, and she got this for $8,000. So one thing is the guy didn't have his WSIB, which I pointed out to her, but she didn't really seem to be bothered by that. But there are things that are going to be more expensive for the homeowner to service in the future. There will be things that are going to negatively impact comfort, and a good contractor, when they're making a fair price, is going to be able to deliver a good product. So, this is just a picture a little bit more focused on that. So this is what's called a low-loss header. It separates the boiler flow from the system flow. This is too small for the flow rate. It's going to work, but the system's not going to be as efficient. It will short cycle. The hot water tank is off to the right of the boiler, or to the left of the boiler when you're looking at it. This is just a 1-inch line. It's really pushing the limit of how much heat you can transfer with that boiler. But because the way it's piped and the piping is undersized, you could end up getting heat going into the house in the summer when the boiler is making domestic hot water, and that's called heat migration or ghost flow. It's a very simple thing, but this is just really sloppy workmanship. You're not supposed to have your electrical connections on the bottom. You just undo these screws, rotate it, put it back in. What else do we have? The B214 code, which is what hydronic contractors must follow, requires isolation valves. So to change this pump, you're going to have to drain the whole boiler. So instead of being, $200 to change a circulator, now in 10 years it's $500 or more, because the guy's got to drain that whole system and then refill it, just to where, for want of, for that size of pipe, like $50 in valves, that's kind of the how you change that. So I want to talk about domestic hot water recirculation. One of the things that we're seeing is that, this is kind of a dumb cartoon, but basically that's a way to reduce the wait time for domestic hot water. In really high efficient homes, we have the opportunity to use point of use for things like sinks. But for showering, we need a lot of hot water, and that requires a fair amount of energy. So my thought is, for the passive house, we should be looking at a storage tank, an air-to-water heat pump with a storage tank, so that you can actually charge that tank in off-peak, because one of the slides I'm going to talk about is peak power is expensive in Ontario. So in terms of energy use for hot water, and I need to do a mea culpa here. I do not have a recirculation system in my house. I've roughed in the line, but I haven't hooked it up. But after I crunch the numbers, I'm actually going to change that fairly quickly. Water is going to be anywhere from 15 to 25% of a house's energy consumption. And this is just standard. This isn't like the passive house, but a typical house. So you're 14 to 25%. And then you're going to be waiting for water, and one of the reasons we're going to be waiting is we've got bigger fixtures which require like a more volume. We've got spas with spa showers with multiple shower heads, and one of the things that I've experienced in what I would call people being very green is that the energy envelope, people are all on board for that. They're all going for higher levels of insulation, spray foam. But when it comes to the bathroom, what are you doing in the bathroom? Just something normal, and you go back and there's like 6 body sprays and like a huge soaker tub. Well, that requires some serious horsepower. So maybe it's a bit out of date, but in 1970, the average home was 1,600 square feet. I think in 2010, it's 2,400. The distance to the furthest fixture has increased 166%, and then the number of fixtures has also increased by 100%. So we're seeing more fixtures in a home, so there's just more pipe, and if you're running it from a water heater to the fixtures, you're going to have bigger volume pipe, and if you're just running, say, a sink in the master bath, you've got to purge a lot of water to get that hot water to that fixture. So the slide that's kind of hidden by this little screen is it's basically showing 6 or 7 fixtures, but what I did was say, well, let's look at 6 fixtures. Well, what's the math behind that? How much hot water do you need? And at 2 gallons a minute, that's you can get lower flow fixtures, but say 2 gallon is well in the CSA limits, so you're 12 gallons a minute. If you had a 100-gallon tank, you've only got 80% of that tank available for you to shower in before that tank gets cold. So with 12 gallons a minute, you've only got 7 minutes before your tank is empty, and then you're out of hot water. So you can, depending what your heat source is, you can shut it off, and if you've got an on-demand system, it can typically, a tankless water heater is going to give you 4 to 6 gallons of water a minute. But just to give you and those numbers are without anything like drain water heat recovery, which I'm a big proponent of because it's very simple. Like, there's nothing to go wrong with it. It's copper pipe. It's going to last for 50 or 100 years, and it's a way to capture that energy that someone has paid for and is flowing down the drain. But if you wanted to run that shower continuously, and this would be just 6 fixtures, not the 8 or 9 that are shown here, you would need 500,000 to 600,000 BTUs. That's 3 tankless water heaters or a boiler with like some whack load amount of storage. And one of the challenges that we're seeing is people don't want to give money or room to mechanical systems. So it's an important thing to talk about with your homeowners when they say, well, what are you going to do in your shower? Like, what are your plans for that? So what does it mean? So we've got more fixtures, more volume. We've got bigger pipe. We've got lower fixture flow rates, and we've got reduced velocity and increased distance. So what's going to happen is we're going to have a long wait for hot water, and I believe it's 18 times longer, well, than, a lot of you are younger than I am, but when I was a kid, you wouldn't wait that long because the house was small and the water heater was close. Well, now, if it's 100 feet, you got to purge a lot of water. In my own house, I have a Navien tankless, which has a little buffer tank. That seems to help a little bit. But one of the other issues with on-demand systems that I'm not sure if you guys are aware of is that every time you turn the water off and turn it back on, the system shuts down and starts back up. And because I come in from the mechanical side, when I shave, I let my water run because it's more expensive for me to pay for the wear and tear on that gas train than it is for me to use the water in that system. So that's one of the drawbacks to an on-demand system is the water waste. So we're wasting water and we're wasting energy. In the city of Toronto, what they've done is they've moved to, it used to get 2 water bills a year, now it's 3. And if you look at that bill, it says the city has approved a water increase of 10% a year, and that's happening every year. So it used to be, I look back a couple of years ago, I was paying $200. This year, I think my water bill is going to be like $600 or $700. So it's not out of the world, but it's something that is increasing. Oh, so I modified this slide from the U.S. Department of Energy because TACO is a U.S. company, but I gave you 3 options. So we've got a natural gas tank, standard of high efficiency, which would be double piped, an energy factor of about 0.66. A tankless, depending which manufacturer you get, an energy factors of 0.9 to 0.95, maybe 0.96. They used 0.9 for a water heater, an electric water heater. I'm not sure if that number is right because when I used to test houses for Enercan, we used to use 0.82, but maybe the insulation's a bit better. So what this is based on is 60 gallons of hot water per day. It comes under just under 22,000 gallons per year. At those efficiency rates, This is the BTUs to heat water from 40 degrees to 110 degrees Fahrenheit. So millions of BTUs. If you want that in kilowatts, just divide by 3,412. In terms of the energy use, so we've got 519 cubic meters for a standard tank, 400 cubic meters for a high efficiency tankless, and 3,371 kilowatts for an electric tank. And I was speaking to Ed about this. My sense, what I did just for simplicity was I took my last electric bill and my last gas bill, and I said, okay, I bought X number, I paid $100 or whatever that number was. I divided by how many cubic meters I used, and it came up with 38 cents a cubic meter. So that includes HST, delivery, everything. Then I did the same thing with electricity, and I said, okay, I use this many kilowatts. How much power did I use, and what's the cost? And I came up with 22 cents a kilowatt. So when you want to compare energy prices, the easy way to do it is to turn that into what's called a therm, which is 100,000 BTUs of energy. So natural gas is $1.15 in the GTA. As you get out of the GTA, like gas I think still stays the same, but electricity prices are crazy. And that's a topic for a different discussion, I think many bottles of wine. But if, based on my calculation, I come up with $6.45 a therm for electric. Propane and oil are about $3.30 a therm. So electricity is very expensive. So what happens is you take your how much you're using times the price, and we get $200 for a standard high efficiency tank. If you have a tank that goes up a chimney, like if someone says, well, I want to save money on the mechanicals, if they have a standard atmospheric tank, that cost would probably go up another 15 or 20%. If you have a tankless, you're about $156, and if you have an electric tank, you're $741 to heat that domestic hot water. Now, this is if you were had 4 people with 10-minute showers at 2 gallons a minute, that's 80 gallons a day. And then there are other factors that would factor into that. So I call this the BGCF, is the bald guy correction factor. So I take a shorter shower than my wife. She has a thick, luxurious mane, so she takes a little bit longer. And those are the factors that are going to, influence your domestic hot water use. Like your kids might take long showers. So a lot of houses, what I'm seeing is we're reducing the heating and cooling loads, but the hot water loads are rising exponentially because people want that spa experience in the bathroom. So when we're wasting hot water, we pay for the water we use, but we're also paying a sewer charge. So based on those water rates, I'm dumping $218 a year down my drain. The gas is $52, and so those are numbers that we can actually do something with. So if I was to, and those numbers are based on $4.47 a meter cube. I'm going to talk to my wife and daughter and see if we can do something about this 0.4 cubic meters of water consumption per day, which, say like when I shave, I'm just letting the water run because it's cheaper than paying the cost of fixing the tankless. So the Department of Energy estimates that people are wasting 12,000 to 14,000 gallons of water a year. That's I think 46 to 52 cubic meters. So for me, that's, if I was to reduce that, I'm looking at $54 to $81 a year as my water saving. When we install a recirculation pump, they are what we call a fractional horsepower motor. So they like a 32nd of a horsepower. So one of the most popular ones we use is what's called the Taco 006. If you ran it for 450 hours at 22 cents a kilowatt, it would be just under $6 a year to run that pump. So this is the way that you can get the most LEED credit for a recirculation system. So we've got a remote activation, so you walk into the room, and when you walk into the bathroom, that sensor picks up the activity, and it's sending a signal to the pump to come on. So you're not running on a timer, you're running on activity. And then what we've got is your hot water comes out of the tank, comes to your fixture, and then there's a way for that water to get back to the water heater to be reheated. And this doesn't have to be a big line. Like this could be a 2-inch line, and this might, well, in a house maybe say a 1 inch or 1 1/4 inch, but this might only have to be a 1/2 inch recirc line. The other thing that's really important, I would say, what I've started to see, Greg lent me his infrared gun one time, and I had a builder that had an issue with a comfort complaint in the summer. And he had, one of the slides I'm going to show you is what's called a home run system. So from the mechanical room, you've got all your branches going up to each fixture individually, and then he has a dedicated recirc line coming back, none of which were insulated. And he's like, the homeowner saying, like, it's hot. It's like, yeah, your air conditioning is not sized for the extra ton of cooling that you're dumping from your water heater into your building in the summer. So this is the way it looks in the system. So you've got your water heater. I wanted to show you this slide, even though it's kind of similar to the other one, because it shows a mixing valve. Some people have the mistaken belief that storing water at a lower temperature saves them energy. Maybe it does, but it actually reduces the volume of your tank. If you store your water hot, you've got a larger volume to mix down and to give you usable hot water. But the other thing that's really critical, and especially for people with young children and elderly people, is it kills the Legionella bacteria. So you want to store your water over 140, but 140 degrees Fahrenheit, which I think 60 degrees Celsius, is an immediate hazard to a young person or an old person because their skin is thinner, and I think it's like 3 seconds and they'll get like second-degree burns with 140-degree water. So a mixing valve will temper that water, and you would adjust that. Now, mixing valves have got a bad rap because there's two types. There's point of distribution and point of use, and a point of distribution allows you to set that water a little bit hotter than 120, but a point of use the valve is manufactured so that it will not deliver water hotter than 120 degrees Fahrenheit. So the challenge with a lot of people, like in new subdivisions, they use these really cheap mixing valves, and they gum up. They don't work really well. They're designed to fail to cold, but people want the water shower a little bit hotter, and if you use the wrong valve, you're going to have dissatisfied clients. But what happens is you've got your hot water that's going out to the building. You're going to have an isolation valve to be able to service your pump. You've got the pump, a check valve that stops cold water from going back into the line because water just kind of wants to equalize temperatures. So a check valve is important. And then you've got your cold water supply coming in, and when the pump is on, it pumps the water back into the tank to be reheated. So I've mentioned a little bit about pipe insulation. So it speeds up the hot water delivery. It's going to, once the water's there, it's going to be hot and available for, the more insulation you put in, the longer that hot water will be available. It reduces the heat loss, and it's saving energy. This is a graphical illustration of that. So if you have uninsulated PEX, to go from, say, 125 degrees when it gets delivered to the fixture, and in 10 minutes, if it's uninsulated, it's dropped down to 115, and probably 15 minutes it's a bit cool. Whereas if it's insulated, we might have like 40 or 60 minutes or an hour and a half where that water is still hot. So I really believe in insulating the lines. It's not a big cost, but it does add a little bit of time to do that. So this is our latest and greatest. It's called the Smart Plus, and what it has is a sensor that gets installed. I won't try my Boston accent, but it learns and adapts how you use hot water in your house. So this is where that fuzzy logic comes in. So there's no programming, as you're wondering, how does it work? So again, we typically get it installed on the return, but it can go on the supply, but you've got a sensor that is mounted to the pipe, and what it's doing is it's the factory mode set to smart mode. So for the first 7 days, it's pulsing that pump for 2.5 minutes every 10 minutes and just sending water out. And when you have hot water, it's going to log that as an event. And it does that. So what happens is at the end of so let's say we had a shower now. Next week at the same, say 30 minutes before, if it's say 8:30 or 7:30, at 7 o'clock, it's going to turn that pump on and it's going to run it for an hour. And then it's going to shut it off. So it's learning your event, and then as you change your habits, it's kind of marking those events and it repeats them, and if you don't follow that cycle, it drops them off. So it's just kind of, a rotating cycle of dropping those events. So it just keeps doing that, and if you go away, then what it will do is after 36 hours of non-use, it will go into shutdown mode, and then it will just cycle the pump. I think it's for 10 seconds every 7 days, and that's just making sure you got some water flowing through the system. If you have, say, a multi-unit thing where people, you can't really determine what that pattern is, then it has a pulse mode, so it's going to turn that pump on for 2.5 minutes every 10 minutes. This is a standard, and we're not exclusive. Like there's Armstrong, Bell and Gossett, there's a number of manufacturers that make recirculation systems. So these are the oldest style, just uses pins, and you set those pins, and you can have they're in 15-minute increments. The pump on the right has a digital timer. You can have eight events in a day. So you can get an aquastat to make your system even a little bit more efficient. So at your furthest fixture, you put in an aquastat, and then it says, okay, I'm hot, and then it'll shut up the pump, even if the pump is still supposed to run, because it says, hey, I got enough hot water here. It's not recommended for tankless units, and the reason why is tankless units require typically a half gallon per minute of flow rate to tell the unit to come on. So if you don't have that minimum flow rate, you can't recirc. The other thing that a lot of people aren't aware of is if you recirculate, if you put the big enough pump in and you recirculate directly through a tankless, you'll take that factory warranty on the heat exchanger from 12 years down to 3, just because that heater is firing constantly. So ideally, if you've got a tankless system, you should be putting in a little electric tank that gets charged by the tankless water heater, and then you pull off that to serve the building. And you're not really heating so you're not heating the water with electricity, but you're just using that tank as a little bit of a buffer. So there are some options, furthest fixture, dedicated recirc line. We also have something called the Genie, which you can put at the furthest fixture, and when someone comes in, you can actually push a button, and that will tell that pump to come on. But that pump is typically located underneath the fixture, which I think is a little bit problematic. Not many people have like a circuit underneath the sink. In a retrofit application, we've got something called the crossover valve, the hot link valve, and basically it bleeds a little bit of hot water into the cold line to allow us to give us that pathway for water to get back to the system. This is the home run system, and when they were first designed, the idea was that we would use 3/8 piping to go from the manifold, which is in the mechanical room, to those fixtures. And when we do that, we've got very small flow rates. But now what we're seeing is, people are using 1/2 inch or 3/4 inch lines. So then you would have to have a recirc line, say, from the shower back to the mechanical room, or use one of those crossover valves. So then we also have something called the smart plug, which will work if you've already got an installed system. Then you can use this. It's got that same learning technology, and you just plug any other manufacturer's pump into that. It's just won an award at the AHR Expo, which is kind of like our Oscars. It mounts very much the same. It's got a couple of operating modes, so it'll tell you if it's in smart mode or pulse mode. It's very easy to install, and that's a picture of the one that goes underneath the sink. And I think we're getting close to the end. So it's got the motion sensor, runs on command. You can use this one with a tankless water heater. Just a little schematic of that. And if you've got retrofits, this is that crossover valve. So basically, there's a temperature-sensitive disc, and it's bleeding a little bit of hot water into the cold line. So it closes when that water is hot, and then, but you need a pump to tell that to allow that water to come through. It's close up of the valve. That's typical installation. So you've got the hot water leaving the heater, going through a sink or a shower. But typically you put that in the sink in a master bath or a bathroom, and then that gives you a way to get the water back to the water heater. We do sell some flood protection things. So these will shut down your water heater, like the gas supply and the water supply. This will shut down the water supply to the whole house, and this one will do just the water heater. That's it. Thanks.